Dear students, today we'll see the following question where it is asked, consider the junction diode as ideal shown in the circuit below. The value of the current flowing through AB is how much? Now if you see this circuit, so here we are having the first point A, so this is A, and here we are having the second point B. So between these 2 points we are having a diode here, and we are having a resistor of 1 kilo ohm. Okay, now here to find the current, our basic formula will be current is equal to voltage upon resistance. Now, what is the voltage between these 2 points? So the potential difference between these 2 points. So we have to find the difference of potential between these 2 points. So if you see, the point A is having potential of plus 4 volt and point B is having potential of minus 6 volt. So if you see the difference of the 2 potential, so it will be plus 4 minus of minus 6. Now this is nothing but plus 4 plus 6. This is nothing but plus 10 volt. So the potential, that is the voltage potential difference between A and B points, will be 10 volt. So if you want to find the current, the voltage will be 10 volt upon resistance. Resistance is 1 kilo ohm. 1 kilo ohm is nothing but 1000 ohm. 1000 ohm. So if you simplify this, 10 upon 1000, it is nothing but 1 upon 100, and this is nothing but 10 raised to minus 2 amperes. So the current here is 10 raised to minus 2 ampere. So out of these options, option 3 will be the right answer. So here if you see option 3, that is 10 raised to minus 2 ampere, is the correct answer. Which logic gate is represented by the following combination of logic gates? Now here in the circuit, we see there are 2 inputs, input A and input B. Now both these inputs are given to NOT gate. So here you are having one NOT gate and here also you are having another NOT gate. Now the output of a NOT gate will be the complement of its input. So if the input here is A, output here Y1 will be equal to A bar. So it is complement of the input. Similarly, if the input here is B, output Y2 of this second NOT gate will be B bar. Now both these outputs will act as input for the third gate, which is a NOR gate. This is a NOR gate. So here the first input here will be A bar and the second input here will be B bar. Now we know that the output of NOR gate will be ORing of the 2 inputs and a complement of that ORing. That is, if you add them, the complement of that you will get. So here Y will be equal to, the output of NOR gate will be A bar plus B bar the whole bar. Okay, now here this expression, if you match with De Morgan's theorem, then we can see that the addition of the complement will be the product of individual complements. So here this can be written as A bar bar into B bar bar. This is nothing but A into B. So Y is equal to A into B, and A into B is nothing but it is a functional operation of AND gate. Out of these 4 answers, the last answer, that is AND gate, will be the correct one. So option 4 is the right answer. So here you can see option 4, that is AND gate, is the right answer. In this question, if in a PN junction a square wave input signal of 10 volt is applied as shown below, the output across RL will be how much? So if you analyze this circuit, this is a circuit where we are showing a diode here. So here is a diode and here is your RL resistor. Now this will be the input of the circuit. This will be the input of the circuit, and this will be the voltage across RL, which is the output of the circuit. So the answer what we have to give is what will be the output across RL. So here we see that the input is a waveform, a square wave, which is having amplitude from plus 5 volt to minus 5 volt. So here you can see, let this be 0 volt, the center line, the 0 line, and here you see plus 5 volt voltage, and here you see minus 5 volt voltage. Okay, so the total amplitude is from plus 5 volt to minus 5 volt. Now, if you remember the working of diode, that is p-n junction. So a diode, if you see, the diode will conduct only when its anode is positive with respect to cathode. So this terminal is called as anode here, and this terminal is cathode. So if the voltage applied at the anode is positive with respect to the voltage applied at the cathode, if the anode is more positive with respect to cathode, then the diode is going to conduct. That means current will pass through it. And only when the current passes through this diode, that current, when it goes through this RL, it will develop a voltage across RL. Okay. Now that will happen only when the input voltage is positive. That means from this 0 line, if the input voltage rises to plus 5 volt and plus 5 volt remains constant here, again it comes back to 0. So this part of the waveform, what is there? Now for this part of the waveform, the diode will be conducting. That means current will pass through the diode, and that current, when it passes through RL, it will develop a voltage across RL. That means the output across the RL will be a waveform which will be from 0 to 5 volt. This is 0 volt to 5 volt. Okay. Otherwise, if the input is negative, if it is 0 and below 0, that is still minus 5 volt, the diode will be in reverse bias. It will not conduct. There will be no current flow, and you will not get any output. So here, because the voltage applied from 0 to plus 5 volt is positive, and in that case the anode will become positive with respect to cathode, the diode is going to conduct, current will pass, and that current, when it passes through RL, it will develop a voltage across it. So the output will be from 0 to 5 volt, and from these options shown below, the first option, that is this 0 to plus 5 volt, will be the correct answer. So here option 1 will be the right answer. So here you can see option 1, that is 0 to 5 volt, that part of the square waveform will be passed through the diode, and that will be seen at the output, and rest other part of the square input will be blocked. So the first option is the correct answer. In this question, the barrier potential of a p-n junction depends on a parameter. A is type of semiconductor material, parameter B is amount of doping, and parameter C is temperature. So the question is asked, the barrier potential of a p-n junction depends on which of these parameters. Now the options for the answers are, the first option says that parameter A and B are correct. The second option says that it depends only on parameter B. The third option says that it depends on parameter B and C only. And fourth option says that it depends on parameter A, B, and C. Okay, now here in this question, we should first remember what is a barrier potential. So if you see a p-n junction, so here you can see a p-n junction. So this is a p-type material shown here, and n-type material. So p-type material will have holes as majority charge carriers. So this is p-type material, which will have holes as majority charge carriers, and n-type material will have electrons as majority charge carriers. And when we join the p-n junction, the p-type material holes will cross over to the n-type region, and n-type region electrons will cross over to p-type region. And as these majority charge carriers move, there is accumulation of immobile ions at the junction. So here you can see the negative ions, and here you can see the positive ions, and therefore we have an electric potential at the junction, and this electric potential is called as barrier potential. Now, what are the parameters on which this barrier potential are depending? So the first parameter what we have seen is the semiconducting material. So if you see semiconductor material, the material called as silicon will have a barrier potential of 0.7 volt, and the material called as germanium will have a barrier potential of 0.3 volt. So definitely this electric potential, what is called as barrier potential here, will depend on the type of material, whether it is silicon or germanium. So the first parameter is on which the electric potential depends. The barrier potential depends. The second parameter says doping. Now doping is one which is adding of impurity to the semiconductor, to the pure semiconductor, to change its conductivity. So it is a process of adding impurity to increase the conductivity, to increase the majority charge carriers in a p-type or n-type material. So if you increase the majority charge carriers, automatically the barrier potential is going to increase. So the second parameter also is one on which the barrier potential depends. And the third parameter is temperature. So temperature is one which we can see that if you increase the temperature, there will be change in minority charge carriers. That is, for p-type material, electrons are minority charge carriers, and for n-type semiconductor, holes are minority charge carriers. So the minority charge carriers, the number of minority charge carriers will change because of breaking of covalent bonds, and therefore temperature also is one parameter on which the barrier potential depends. So out of the three parameters shown in the question, whether it depends on semiconducting material, or it depends on doping, or it depends on temperature, so we can say that the barrier potential depends on all the three parameters. So here you can see the explanation. Barrier potential depends upon, number one, materials used to make p-n junction. That is, for silicon it is 0.7 volt, and for germanium it is 0.3 volt at room temperature. It also depends upon amount of doping done, because the amount of doping will decide the amount of majority charge carriers in the junction. It also depends on temperature, because increase in temperature will change the number of minority charge carriers. So here in this option you can see option 4, that is the parameter A, B and C all stands true. So the barrier potential of a p-n junction depends upon all these three parameters. So option 4 is the correct answer. So here in this question, in an n-type semiconductor, which of the following statement is true? And the options are: option number 1, electrons are minority carriers and pentavalent atoms are dopants. Option number 2, holes are minority carriers and pentavalent atoms are dopants. Option 3, holes are majority carriers and trivalent atoms are dopants. And option 4, electrons are majority carriers and trivalent atoms are dopants. Now, if you remember the formation of n-type of semiconductor, so when we are initially having a pure semiconductor like silicon or germanium, and we want to convert this pure semiconductor into n-type semiconductor, then we have to add an impurity which is pentavalent in nature. So if you add an impurity which is pentavalent in nature, then we will get n-type semiconductor. N-type semiconductor. Now, when we add a pentavalent impurity and when we get n-type semiconductor, in n-type semiconductor, the majority charge carriers will be electrons. The majority charge carriers will be electrons, because we are adding a pentavalent impurity to a pure semiconductor. So majority charge carriers are electrons and minority charge carriers are holes. So holes will be minority charge carriers. Okay. So with this background, if you see these statements, so the first statement says that electrons are minority carriers, which is false. Second statement says that holes are minority charge carriers, which is true. And pentavalent atoms are dopants, that is also true. So out of these four options, the option number 2 is the correct answer. That is, in an n-type semiconductor, holes are minority carriers and pentavalent atoms are dopants. So here you can see option 2 is the right answer. Holes are minority charge carriers and pentavalent atoms are dopants. Now here in this question it is asked the output X of the logic circuit shown in the figure will be what? If you see this figure, now in this figure A and B are the two inputs, and we have a NAND gate, and after that again we have a NAND gate, and there is a output. So here if you see, A and B are the two inputs here. A and B are the two inputs, and this is a NAND gate. This is a NAND gate. Now we know that the output of the NAND gate will be, in terms of inputs A and B, here will be A into B the whole bar. Okay, now this is given again to another NAND gate whose inputs are shorted and it has been made only one input. So A into B the whole bar will be the input for the second NAND gate. Now this NAND gate is going to act as NOT gate, and here the output will be A into B. So here the output X will be A into B. Now this output is shown in option 2 over here. So X is equal to A into B will be the right answer. So here you can see X is equal to A into B is the right answer. Now here in this question, the figure shows a logic circuit with two inputs A and B, and the output is C. The voltage waveform across A, B and C are given. The logic circuit gate is which one? The options are AND gate, OR gate, NAND gate and NOR gate. Now if you see the voltage waveform here, so this is your A input, this is input A, this is input B, and this is output C. This is output C. And if you see this voltage levels, so in the first time interval, this is the first time interval, this is the second time interval, this is the third time interval, this is 4 and this is 5. So if you see in the first time interval, A is high, that is logic 1, B is low, that is logic 0, and C is high. If you see in the second interval, A is high, logic 1, B is also high, and C is also high. If you see the third one, A is low, B is high, and C is high. If you see the fourth one, A is low, B is also low, and C is also low. And then if you see the fifth one, A is high, B is low, and C is high. Now if you arrange this as a truth table, so A and B are the inputs and C is the output. If you take the first one, A is high, B is low, and C is high. And if you take the second one, A is high, B is high, and C is high. If you take the third one, A is low, B is high, and C is high. If you take the fourth one, A is low, B is low, and output C also is low. So these four combinations are enough for us to identify which is the logic gate. So if you see this truth table, you can see that if any one of the input, or if both the inputs are high, the output is high. So in the first three cases, these three cases you can see, here one input is high, in the second both the inputs are high, and in the third one input is high. For all these three cases, the output is high. And we see in the last a combination when both the inputs are low, the output is low. Now this kind of a truth table gives you the performance of a OR gate. So it is performance of a OR gate, which says that if any one of the input is high, or if both the inputs are high, the output is high, and when both the inputs are low, the output is low. So out of these four options, option 2 is the right answer, that is the OR gate. So here you can see option 2, OR gate, is the right answer for this voltage waveforms. So here in this question, gate and output Y is equal to 1 in given circuit, which of the following input will be correct? So if you observe this circuit, now this circuit is having three inputs. These are three inputs, A, B and C, A, B and C, and here you are having a OR gate, here you are having an OR gate, and here you are having an AND gate. Now output of this OR gate will be, the OR gate is having two inputs, that is A and B, so output will be A or B, and output of this AND gate will be, the A or B is one input and C is another input, so the output will be here for AND gate, that is A or B into C, which will be equal to Y. Okay, now for Y is equal to 1, for Y is equal to 1, which is the condition asked in the question, it is important that out of these two terms, no term should be 0. No term should be 0. Say for example, if A or B is 0, the output will be 0, or if C is 0, output will be 0. Now with this a condition, if you see the options given, then we can see that in the first option C is 0. C is 0. So this cannot be the combination for which you will get y is equal to 1. In the third option again C is equal to 0. So here also you are not going to get y is equal to 1. And in the fourth option here also it is C is equal to 0. So you cannot get y is equal to 1. Now only in the second option you can see A is B, A is 1 and B is equal to 0. So A or B is equal to 1 or 0 is equal to 1. And C is 1. So 1 into 1 is equal to 1. So y is equal to 1. So only option B satisfies the condition so that the output y is equal to 1 for this a combination of the inputs. That is, when A is equal to 1, B is equal to 0 and C is equal to 1, we are going to get output y is equal to 1. Okay, so here you can see option 2 is the right answer, where A is equal to 1, B is equal to 0 and C is equal to 1 is the a combination when you can get y is equal to 1. So here in this question, it is asked the device that can act as complete electronic circuit is what? Options are Zener diode, junction diode, integrated circuit and junction transistor. So if you observe these options, then in these options you can see that the first option, that is Zener diode, is a device, or it is a component. It is a component, so it cannot be a complete electronic circuit. The second, a junction diode, is also a device or it is a component. The third, integrated circuit, is a complete electronic circuit. This is a complete electronic circuit. And the fourth, a junction, a transistor, is also a device or a component. So from these four options, option 3, that is integrated circuit, is the complete electronic circuit, and this is the answer for this question, that is integrated circuit. So here you can see the device that can act as complete electronic circuit is integrated circuit. So in this question we see that which one of the following statement is false. So options given are: the resistance of intrinsic semiconductor decreases with increase in temperature. Obviously it is true, because as the temperature increases, the covalent bonds will break, and as the covalent bonds break, there will be movement of the charge carrier, so the resistance will decrease. Second option says that pure silicon doped with trivalent impurities gives a p-type semiconductor. Obviously, when a pure semiconductor like silicon or germanium is doped with a trivalent impurity, the output of that is an extrinsic semiconductor, which is p-type semiconductor, because number of holes will increase. The third option says that majority carriers in a n-type semiconductor are holes. This is wrong statement, because majority carriers in a n-type semiconductor are electrons. And fourth option says that minority carriers in p-type semiconductor are electrons, which is true, because in a p-type semiconductor, majority charge carriers are holes and minority are electrons. So out of these four options, option 3, where it is saying that majority carriers in an n-type semiconductor are holes, is wrong, because majority carriers in n-type semiconductor are electrons. So option 3 is a false statement out of these 4 statements. So here you can see option 3 is the right answer for this question.